Yeah, it's APS Physics, the March meeting, starting this morning.
Oh, okay. You going?
Yeah, I've got a virtual, going virtually.
Okay.
So I've got at 11:30 mechanobiologies of cells and tissues, live streamed. There's more, I don't get to go to all of them. Like there's, I don't know.
Right. We have a full slate. All right. Yeah, welcome. Yeah, hi, Vahid. How are you?
Hi, thanks. I'm fine.
Here's Mohammad. Well, Mohammad.
Hello.
Oh, hello, everyone.
No.
Would you like to introduce yourself, Mohammad?
Yes, I do research in swarm intelligence and evolutionary computation, and I've done some work on image reconstructions.
All right, great. Welcome.
He's also a master of blights. He has a whole flock of them in his backyard.
Oh, yeah.
It helps. It helps with the students.
Yeah.
Inquisitive students that force.
Yeah, you need something to feed them.
Yeah.
All right. So yeah, Vahid wanted to give a talk here. So this is Vahid Ghayoomie, and he's been involved in OpenWorm for quite a few years. He's been doing a lot of things with ion channels and modeling there. And let's see what he has to say.
Okay, thank you, and hello everyone again. Actually, we're going to have it maybe somehow a weekly talk on some progress on any major reconstruction work that represented by Dr. Gordon some time ago. So firstly, I asked him because actually he's an expert now in this project and the book he's writing. I asked him earlier that if he could start with the introduction, because I guess we had some introduction in the past, but because since Mohammad and maybe some newly, could you please have 1 or 2 minutes introduction to the project? Because I'm a little familiar. Yeah, these days, actually, since I'm newly added to the project, I'm going to start with the image reconstruction, but before that, would be happy to have your introduction to the.
Okay, here's the basic. Can you guys see the whiteboard?
Yes.
Yes, okay. It's the basic problem. Take a square image.
I can also share.
I don't
I
see
can also share the.
Okay, no. X. Okay, now how do I get a square? There we go, square. Okay, take a square image. You shoot X-rays into it. Let's see, I gotta get a line here. You shoot X-rays into it, that's supposed to be a straight line. And the X-rays in the detector over here. Okay. This is what we're after. What's different in ordinary computed tomography, X-ray computed tomography, you either use a fan beam in 2 dimensions or a cone beam in 3 dimensions. In other words, the X-rays spread out throughout the patient, and you hope to image some problem in the patient. Now, this means that ordinarily in CT, you're irradiating a lot of normal tissue. Okay? What we're trying to do is minimize that. So what we do is, instead of a 2-dimensional fan beam, which would go like this, or a 3-dimensional cone beam, which will look like that, we're just going to send one line in at a time. And the reason we can do this is that we're using what are called polycapillary X-ray sources, which have been pretty well perfected over the last 20 years. Vahid can you'll show the principle of the polycapillary. Okay.
Yeah, actually, I'm trying to open your presentation, the last one. But yeah, could you have the slides as well, because your slides is not very well in my computer.
No, I don't have them on this computer. That would waste a long time trying to get it up. So
Okay.
if you want to show it, that's fine.
Okay,
I sent you the PowerPoint. Okay, so basically what we have is a line across the patient. And then we'll aim at another angle, and we got another line. Okay, now we have an interesting problem here. And that is, can we reconstruct the whole square from a couple of lines? Okay, or what is the minimum number of lines that will allow us to do that? Oh, there we go. Oh, okay. What I call for next slide.
Okay. Actually, I'm sorry because it's not very. It's a PowerPoint. Windows-based one and on Mac, it's not showing very well.
Well, just start at the beginning, and I'll ask you for the next slide. Just a second. I'm going to close the door so I don't hear the dog barking.
Okay.
Okay, go to slide number 2. Okay, so what we're trying to do is a variation on breast compression mammography. Now, the geometry of this is quite simple. There's an array of detectors at the bottom and a transparent plate at the top, and you send x-rays through the top and onto the detector, and you reconstruct the breast in between. Now, 25 centimeters is chosen as an industry standard for these compression paddles. So the breast is compressed typically to about 5 centimeters in this mammographic apparatus. Okay, the detectors typically have 1/10 of a millimeter size, so it's a very large array, and the total size is to take the biggest breasts that are known. Okay. So this machine will take any size, including one that fills the whole space. Okay, next slide, please. Okay, so this is the new apparatus that is used. It's an X-ray source. The box on the right hand side is the X-ray source with a fan to cool it. It focuses it on to a set of glass capillaries. So it's called a polycapillary X-ray source. And the idea is to aim it at any angle up to this in any position in this 25 by 25 centimeter square. Okay, next slide, please. Okay, this is the general principle. The blue lines represent the polycapillaries. The individual ones, the X-ray source hits them. They are heated so they can be curved, and in this case, they come out parallel. The X-rays come out parallel to each other, and it's a very, very small angle of spread in this thing. I think they get 0.04 degrees, something like that. So they're effectively very parallel. Next slide, please. This shows the real polycapillaries. If you look at it on the left, you can't see them. They're very tiny. They're about 10 micron inside. And if you magnify them, then you can see them, the individual ones. So it's a huge array of polycapillaries. And the X-rays can be bent because they do what's called total reflection on the surface of the glass. So these capillaries just have air in them. And the X-rays come out then through these 10 micron capillaries. So that's the basis of the polycapillary source. Next slide, please. Okay, so what we're going to do is test this idea. Here we take a black and white picture of a butterfly. Next slide, please. And what we're going to do is we're going to extract alias lines of pixels across the picture. Now, this is a preliminary to doing X-rays. So here we use the aliased version of lines rather than the more common anti-alias straight line, which has grayscales along it. The anti-alias straight lines look better. The alias straight lines are either black and white or white, so we use them to select the pixels from the butterfly picture, okay, along the line. You'll notice that the steps are not equal in size. Some are 3 here and some are 2 in this example. Okay, next please. Okay, so here's a bunch of parallel lines going from top to bottom, representing the top of the top pedal to top rest pedal at the top and the detectors at the bottom. Here we're just doing 2 dimensions. And I don't know if you can imagine it, but you can barely see the butterfly. Next slide, please. Okay, if we do a very simple form of inpainting, which is just an interpolation between non-zero pixels in a row, you can start to see the butterfly, even with this kind of lines. Next, please. Okay, now, most inpainting is done to remove lines. For example, this bird gets out of the cage if you remove the cage. And, so inpainting is usually used to remove lines you don't want. What we're doing is the opposite. We only have lines and we're trying to fill in between the lines. Okay, next slide, please. So this shows, let's see, S is the power of 2 for the number of lines we use, going top to bottom. And you can see that the Euclidean distance to the butterfly is much reduced if we use even our naive simple inpainting algorithm. Next, please. Okay, now here we try random lines. Again, you can barely see the butterfly. Next slide, please. Okay, so here's a number of lines. We always add 2 lines, which are basically the columns on the left and right side. So it's 2 to the 6 plus 2. So it's faintly visible. Next, please. If we do the inpainting, you can see the butterfly. Okay, next, please. Okay, and even with random lines going from top to bottom, you can see the Euclidean distance to the butterfly is much lower than just the lines by themselves. Next, please. Okay, so this is, okay, what we're faced with here is a challenge. If you try to search on CT algorithms, you'll find thousands of papers for both the fan beam and cone beam. But you'll find absolutely no papers at all on what we call ray-by-ray computed tomography. No one has done it. So we have a new challenge here to do computed tomography 1 ray at a time. Okay, next slide, please. Okay, so this is just showing what the fan beam and the cone beam look like. And on the right is, again, our aiming a single ray. Next, please. Okay, now the problem, well, go back 1 slide. Go back to the previous slide. The problem with fan beams and cone beams is that they irradiate everything in their path. And so whether it's normal tissue or the tumor, it all gets irradiated. Now the problem with breast imaging is that breast is very sensitive to X-rays, and you can actually cause tumors with it. So what we're trying to do is basically we're trying to image the tumors with minimum imaging of normal tissue. Now I can make an analogy. Is there anyone who doesn't know what a shotgun is? No answers. Okay. Now, shotgun shoots a whole bunch of small pellets, let's say at a flock of birds, and you hope to hit a bird and get at least one out of the flock. And basically, that's what fan beams and cone beams do. They radiate, they blast X-rays out in a whole sector or volume, and you hope to find the tumor in there. Okay, you all know what a rifle is? A rifle shoots just one bullet at a time, but you have to have it precisely aimed. Okay, so the analogy here is that we're trying to turn X-rays into a rifle source instead of a shotgun source for the X-rays. Next slide, please. Okay, now, before you go reading that, it shows what a focusing polycapillary source looks like. And it has a bunch of polycapillaries again, but they've been bent so they come to a focus. Now, the advantage of this is that it puts a lot of X-rays at the focal point and very few at the exit of the polycapillaries. So it can actually, there's one report on using a focus source, polycapillary source, to kill a tumor in about 1 minute. So it's a practical way of destroying or ablating tumors by focusing on them with minimum damage to the normal tissue. Okay, now, obviously we need better in-painting algorithms, possibly including machine learning algorithms, which, to be honest, are over my head. What Vahid has been working on is what we call independent image processing.
Can you see me?
Yes.
Yes, now we see it. Okay.
Okay. So during the past 2 or 3 months, actually, I was working maybe 10 to 15 hours per week on this project for seeing how we can help with the image reconstruction. Beside the past week, that I was encountering a bug in the Python version of Shapely that actually took a week of me to figure out what was wrong with the Shapely, a famous library in Python that was actually I was dealing with lines and points. But in general, I started with a new in-painting algorithm, the previous one that Dr. Gordon mentioned, especially with the method for generating a line based on previously generated lines and their pixel values. There was actually the problem was that these type of line generation usually tries to find some new points or pixels which have actually the risk of being stuck in some some points. As you see here in the left and rightmost parts of the picture, it could not find any lines, so the picture is not in-painted fully. So I was trying to work on firstly on a better maybe in-painted algorithm. I used OpenCV, a very famous in-painting algorithm in Python, which is using Navier-Stokes algorithm. The problem with general purpose in-painting algorithm is that they usually, as Dr. Gordon mentioned, they generally try to find something which is missed in a picture, so to in-paint it and recover the image. So they usually have the full image and with some, for example, lines that try to remove those lines or something like that. But here we have a problem which is vice versa. We have some lines and we are trying to complete the lines between them. So I used the tweak somehow for using the OpenCV. I converted a line, actually an image with some lines, into a background image, which is everything within, and the lines are now being considered as some new image. Actually, here the lines are image. So here the black background is going to be disappeared and replaced by some pixel values in between. As you can see here, I could impaint it using this algorithm, using actually the OpenCV and Navier with some default. The first try was that I believe it could be possible maybe that we could have some masks from left to right as well, because here our actual devices only allow us to have some lines from top to bottom, but maybe in the future we could have this as well. So I tried the first time some lines from left to right as well, and got a better result with the imprinting with the same algorithm in the past. Actually, some better results. Then, as you can see, the image is much better than the previously generated image. But considering the available appliances and devices, I tried in the next tries, I tried to have only the bottom or top to bottom lines. So here again, I tried to use a new algorithm which is trying to find every possible polygons within the
Vahid, you cut out. Can't hear you.
Yeah, I think we'll have to wait for him to get back online. He might have gotten dropped.
Yeah, let me explain something. We're sticking to the standard rest compression geometry, which is why we only consider lines from top to bottom. And the difference between reconstructing this butterfly and reconstructing the X-ray image is that with the butterfly, we're extracting all the pixels along the line, so we know their individual values. With X-rays, to a first approximation, we won't know those values. We will only know the average value along the line. And so we need to both reconstruct along the line and do the inpainting to get the rest of the image. So the goal which Vahid is working towards is to try to find an algorithm for choosing the next line that you aim across the patient. And the fewer the lines we can use, the lower the X-ray dose. Okay? So that's what he's after. Now, when we get him back, I don't know.
Right.
Okay, Mohammad, you can see that perhaps a White approach could do both reconstruction along the lines and reconstruction between the lines, which would be the inpainting.
Yeah, this is interesting. I'm trying to understand the kind of inpainting that Vahid has used in his work, and if there is a way to use a fitness function to see the quality of the inpainting, and
right. We've been using just standard Euclidean distance between the inpainted picture and the original.
Okay, but this is something that you would do only towards the end to see the quality of the reconstruction, not throughout the process.
You can calculate it at any time,
but that wouldn't be that wouldn't be realistic. It would be an issue because obviously we don't have access to the original image in reality when doing X-ray, but we do have access to the receptor's value. So that is something that we have access to. And
the approach we're using is you're right. We don't know the original with the X-rays, but if we can't reconstruct it, but we do know it, we know we don't have a good algorithm.
No, exactly. So trying to see what the fitness function is based, that would be helpful. So basically when you're projecting one line and you have part of the image reconstructed, is there another way of comparing? So for example, we can use the if we take the, I don't know if you're familiar with, I'm not very familiar, but if you're familiar with MRI, we have the image space, which translates to K space, and then we can compare the distance between the K spaces.
Is K space a Fourier transform?
Yeah.
Yeah. Okay.
Yeah. So in a way, we have a measurement where we can see what the image similarity is, but not by looking at the image, by looking at the K space, which is the inverse transform.
I got you.
So if
we haven't tried that. Yeah, we haven't tried that.
So if we have if we use single array projection and we have an image reconstructed, instead of comparing the images, if we have a way of saying what is the quality of the reconstruction without having to compare it against the original one, then it would be it could be useful.
Could be.
And that would be our fitness function. And if we have that, then we can use swarm intelligence and evolutionary computation to basically optimize the process.
Okay. Except what do you use for your data set for machine intelligence?
So I mean, at the moment I'm using the signoids, which is basically what we have. Let me see if I can. I don't know if I can.
You mean the sonogram?
Yeah, the sign. Okay, so yeah, so you know, yeah, of course, you know the sinogram is the measure for comparison at the time being, which is again exactly what we have access to, and we try to reconstruct from the sinogram.
Okay.
So if we can have a measure along that line, then we can basically apply some of these methods with not so much difficulty, and also without having to use the image itself, which would not be accurate, because if we use the images, then it would be very easy to reconstruct the image in a way, because you have in a way your optimization would become unimodal instead of multimodal, which makes the problem much easier in principle.
Yeah. By the way, you're familiar with the MART algorithm, MART?
I haven't come across it, but I've seen it in your
okay. The MART algorithm could do the reconstructions along the lines. Okay, because it is based on lines. So you could just confine it to the lines that we know. Okay. Now there are many ramifications of this. The simplest approach is just replace the pixels along the line with their average along the line.
Yeah. So this is an imprinting technique, but would we be able to use the sinogram style for the imprinting? Because obviously you're projecting array and then you're reconstructing along the line by putting the average value or any other way. Then that could be a fitness value. That could be a way of seeing how similar are we to the original.
I'm not used to that. I've always worked in real space.
Sorry, say again?
I've always worked in real space. I've never attempted to use the sinograms.
Okay, so that's one thing we need to find out.
Yes.
How to compare the images.
Yeah, I didn't say we know everything here. What Vahid has been concentrating on is how do we choose, is there an optimal way to choose the next line?
Yeah.
And this becomes, at every step, it becomes a picture-dependent image processing problem.
Yeah.
Okay.
Yeah. I don't think it's a difficult problem, but I was wondering if there has been a choice on that, because once that is done, then well, I'm curious to.
No, we haven't unless he's succeeded lately. I'm not familiar with. I tried a very simple algorithm, and it did not produce better results.
Okay.
So he's trying to find something better. Now, one thing that we have going for us is that we're looking for small tumors, which means they're around 2 to 4 millimeters in size. And remember, we're dealing with 0.1 millimeter detector pixels. Okay, so a small tumor is likely to be more circular, and we could use a template approach also, where we look for tumors that may be showing up well enough so that they could be located by a template.
Yeah, which is great, because I think these fine tuning could happen rather nicely towards the end, once there is a solution created. Having those prior knowledge, yeah, absolutely, yeah.
Okay, Vahid, are you ready to go again?
Do you have my screen?
No, it didn't.
I got
unshared.
disconnected. I got disconnected for a while.
Yeah.
Okay.
Must be a sandstorm in your case.
It's somehow usual now over here.
We have lots of snow outside.
Okay. Did you ask anything from my side? Because I didn't have you for 1 or 2 minutes.
Oh, we were discussing, Mohammad was suggesting other approaches to reconstructing the images when you don't know the original.
Okay, yeah.
There will be some question, Vahid. I'm curious to see what you've got in your work, and it seems like an interesting work. So we were just discussing some components around the work, either pre or post, and but we'll discuss that hopefully after your
for sure. Because my next tries are going to be based on some deep learning based algorithms for considering a range of pixels that every new line is going to be to add to the previously generated or regenerated pixels. So that would be a more complex one. But the unique thing about this project is that actually in compare with other imprinting algorithms, we usually in other imprinting algorithms we have much more data from the pictures. We have all the pictures available, and we are trying to do something else. But here we usually work with sparse matrices, and so it's a little different. We are trying to have as less maybe as possible number of lines to find the best or the optimum image that could be reconstructed. I have one more point that I mentioned somehow, but I would need some answer from Dr. Gordon for other works. I will ask him later maybe. But the point is how much, because that was really different for my works, how much a width of a ray or of a beam effective for actually this one. Do you have any exact measurement of the width of a beam? Is that, for example, 1 pixel width wide or?
Yeah. For now, now we're assuming the beam is just 1 pixel wide, but the real beam can be up to 1 millimeters or so wide.
Yeah,
Okay? But the diversion, what do you call it? The spread of the beam is very low.
because that's yeah.
In the worst case, it's about 2 pixels.
Okay,
Okay?
so
It's
that would be really different because array with 2 pixels, actually, if we are considering, for example, 64 lines and array with 2 pixels, that is 2 multiplied by 64 lines.
Yes.
Not one. Yeah, but and that could really make a lot of difference in our measurements as well.
Yeah, let me open the chat here. I have
Okay,
a paper.
I will discuss it in detail later, maybe in our opinion, because I guess it's a little detailed work and maybe it's not so much interesting for others. Could we have actually Mohammad what he was what the point was making and finish that topic as well? Sorry.
No, that's okay. I think Vahid, if it's it would be great if you finish your presentation and then we'll get back to that because it's not something. So I don't know if you finish your presentation because
actually it was finished and I had some minor points that something like what I mentioned right now, but the others are more detailed works that we could discuss later as well.
Okay.
Okay.
Vahid, let me just point out, I wrote a paper many years ago on what I called voxels. And voxels are where you use a parallel set of beams that are grouped together and reconstruct from those instead of a single line. So we like having a bunch of parallel lines.
Mm-hmm.
And it worked very well. That's all I can tell you. It's okay.
And one more thing, I guess a very important. I discussed it once before, but I know that maybe Mohammad has been dealt with something like that in the past. A very important parameter here is, or method is to be considered is the evaluation metrics. We are using Euclidean distances, but when you have, for example, something like 25, maybe 1,000 pixels or 250,000 pixels, we can say, the distance between them, and especially the distance between the most prominent points, is much more actually important for us to be evaluated correctly, because our matrices are usually sparse matrices, and when we are comparing an image with something that is simulated, we are actually purposefully simulated because we are looking for something in the future, like tumors or something like that. So some sections of the image are much more important for us than the backgrounds, something like that. So the evaluation method is really important, I guess. I had some experiments in this one that only one line could have something like 1% difference in the actually final result. That was really high. So I guess we should first of all agree on the distance measurements and the evaluation criteria, and then try to find the best, actually the optimum algorithm that we are looking for. And this is something I actually I had a lot of problems with during the past weeks of work. So I guess that would be a really important point to be agreed with editors.
Yeah, happy to take that. Or Dick, would you like to say something to that, or shall I?
Well, this is a very strange form of computed tomography. As I said, there's no literature whatsoever on it that I can find. Okay, so we have a chance here of developing a whole new set of computed tomography algorithms the aim of which is lowest possible dose to detect tumors. Okay. Now, one thing that about the lines is kind of curious. Suppose you detect a possible tumor. If you aim more radiation through it, the picture of that tumor should improve. Okay. Now, it can improve in two different ways. If there's a real tumor there, you'll start to see it. If there's no tumor there, it will fade to background. Okay, so that's one of the things about it. Yeah, another thing is that since we're going top to bottom, it means the distribution of angles is narrow compared to full circle. Okay, so we're going to have some vertical distortions, which can possibly be removed by deconvolution. Okay, we've shown back in 1984 that for standard computer tomography, if you deconvolute the image, you get a much improved image. If the angle range is narrow. So that's a possibility. There are other things that we need to consider. That is that the breast can be characterized by what's called Perlin noise. Let me take that in. Perlin noise. Okay. Perlin noise is kind of strange, but it seems to be characteristic of the texture of normal breasts. Okay. So it provides the background against which we need to detect the tumors. And so we need to introduce Perlin noise and see if what it takes to detect the tumors. There are other things we can do, such as increasing the contrast of tumors. This can be done by using chemicals that concentrate in tumors, or by using what's called the K-edge of iodine. The K-edge means a sudden jump in the absorption coefficient of X-rays between one wavelength and another. So if we take two images with our lines, one below this K-edge and one above it, and take the difference between them, that can show up tumors. Okay, so there's a lot of interesting things to do here. And as I said, also the Foxwell's approach would be more realistic because we're dealing with a beam rather than a narrow line of X-rays. Okay, so we're trying to work up to the realistic case.
Yeah.
Okay.
So back to your question, Vahid, in terms of the comparison and the Euclidean distance or other measures, there are other measures. I think it's not that important at this stage. You can stick still to the Euclidean distance as a measure. What we were discussing when your line dropped, we were talking about the actual image similarity that you're trying to access during the process. So during the image reconstruction, obviously you start with projecting one ray, and then you would start the image reconstruction, and you have obviously with one ray you have an infinite or near infinite possibility for a reconstruction.
Yeah.
And then you add in project the second ray, and then you try to limit that possibility of the reconstruction. So you'll continue with that. But in terms of these infinite or near infinite possible reconstruction, what would be your measure in terms of choosing which one is a better one? So how do you pick the high or better reconstruction in terms of all these possibilities?
Actually, the only metrics currently we are working with is the Euclidean distance, and I'm trying to add some pre-processing to image as well. Like, let me see if I can share my window. I've been using some thresholds for because we are working with grayscale image as well. Something like this is somehow making some thresholds on the image. Actually, this is something for the next level, because in the next level we are working with the supervised, I'm trying to find out if it would be possible to work on some supervised algorithm. The supervised algorithm, we could find something like this. If we consider these spots on the wings of the butterfly similar to some tumors, I could actually make some pre-processing on an image like this to find out how we could better deal with those spots on the wings of the butterfly. So similarly, we could find the tumors as well in this way, and more specifically to how to concentrate on some tumors like this. Because when we are regenerating an image or painting an image, we are more interested in discovering and as much as possible some points like that, some images, some parts of the image like this. So I'm hoping in the future, if we could have a good data set, we might be able to learn from some realistic image, and then we could have some better supervised algorithms for finding, for not only in painting algorithms but also a data-oriented painting algorithm in a way that we could actually generate the best possible image of that sections of the image that we are interested in, especially.
So on that, Vahid, what I was going to say, there's an echo. What I was going to say is that when you are, so the reason why I asked you how you pick the best reconstruction from an infinite number of possible reconstructions is to find out what is your measure. Obviously, you have the ground truth, which is your original image.
Mm-hmm.
So the original image you should not be using during the reconstruction process. So there should be a different measure that would tell you how far you are from from your target reconstruction. If you use the original image, it means you have the original image, which means that there is no point in the reconstruction process. So the intermediate process for evaluating which reconstruction is better should be a different one. I can give you an example.
Yeah. I know where you're going with this topic, but here, because when we are, if I'm right, Mr. Gordon, please correct me if I'm right. If I'm wrong, when we are actually when we're having a ray or a beam, the beam is going to detect what is in the way from the source to the detector. So we have, for example, if we have a vertical line, for example, from top to the bottom, we have 512 pixels detected by the beam. So
you have actually only one value, so you don't have access.
No. We have 512 values, new values, because the beam is detected on the bottom, on the detector part, and it can approximate the value of the pixel that the line or the beam has been detected. So we have from a range of 500 multiplied by 500 possible pixels, we have with a vertical line, we have 512 pixels detected now. So every time we are having a new line, we have some values in the past that we could actually decide based on them.
Well, Mohammad, maybe I should make something clearer. The reason we're dealing with the butterfly picture is to see, can we reconstruct the butterfly from lines? Now, in this case, we know all of the pixel values along each line. And we regard that as a subset of the problem of X-ray computed tomography, because in X-rays, we only know the average along each line at each pixel.
So in this case, when you project one ray, do you have access to the values of the entire pixel sets that ray has visited?
Yes, we do.
Okay.
In the butterfly example. In the real X-ray example, we only have access to the sum of the pixels.
Right. So this is what I was trying. Yeah, exactly. Yeah. So if we have a toy problem, then obviously we try to get as close to to the actual scanning situation, which wouldn't be a waste of time. Actually, we would be on target. But so basically, on a scanner, when you project one ray, would we be having one value at the end, at the receptor end? Okay.
Yes.
So yeah.
Instead of 512.
Yeah. So this is what I was trying to get to, Vahid. That we don't have access to those pixel values in the real world. So if we assume that we have access to the 512 pixel values, then we would be dealing with a different problem, not the reconstruction problem.
Well, we regarded the butterfly problem as a subset of the real problem.
Yeah, no, the butterfly problem is fine. It can. Okay, can I use the whiteboard just to?
Sure, go ahead.
Just to explain. Okay, so I hope I can draw something, and so basically, I hope you can see the whiteboard.
Yes.
Well, we'll tell you when.
Okay, so this is the. So if we imagine that this is the. This is what we're trying to reconstruct. So we have this object inside the square that we're trying to reconstruct, and if we project a ray at the end here, we have one value. So basically, if we assume that we have this is a butterfly basically, and we have a ray that is projected from the top, and then at the end we'll get a value here. Let's call that x. So this is the only value that we have access to, rather than the individual pixels.
Right. In
the real problem, yeah. So one way of seeing the reconstruction, that we are close to the original reconstruction, is to give these pixels certain values.
Yes.
So we give these pixels certain values, so that assuming that this ray is giving us the sum of all the pixels along the way, then we try to put these pixel values here, and then we compare it against the detector value at the end.
Yeah,
and then we would.
That's what the MART algorithm will do.
Yeah. Okay. So that's so this could be the measure, Vahid, if you're with me as well. So this would be the measure in terms of seeing how similar the reconstruction that we have is with the original image. So basically, we compare this x, and if we have so if we assume that this is the original image, and then here we have the reconstructed image right here, and then with the reconstructed image again we do the same thing, and then we collect and we calculate all the pixel values, and then we'll have, let's say, x prime. The way that we can tell how different the reconstructed image is from the original image is by taking the distance between x and x prime.
Yes. Mohammad, there's one problem here.
Yeah.
And that is that the MART algorithm is iterative, and it drives x minus x prime to 0.
Yes. Yeah.
Okay.
Yeah. So it's trying to reduce that distance. Is that what you're saying?
Yes, it reduces that distance to 0 if possible.
Yeah. Which is what we want in a way for reconstruction. With the caveat that we know that the system is underdeterministic.
Oh yes, correct.
Yeah. But this is the measure that we have.
Oh, that's the Euclidean distance between the two.
Yeah, and then we have the distance between the two single values rather than the pixel values.
Now, let's see. Let's see. Stroke, fill, stroke width. Oh boy. Oh, hey, here we go. Okay, we have two algorithms I would recommend. That's MART and what's called power. Okay. That's what I'd recommend. Of course, you haven't done the infilling yet. So the question is, how do you do the infilling in an optimal way when perhaps using Mark to get values along the lines, then what do you do in between the lines?
Yeah. What we have been done so far is actually somehow interpolating or painting between lines that have been estimated in the past using something like Mart or Power Mark. So we have something like 512 values, estimated values for each beam, which is actually estimated by an algorithm like Mart or Power Mart. And after that, we are going to decide what could be in between of those lines.
You see, for Mart, suppose we take another line like this. Where these two lines cross, the pixel values should eventually be identical after another iteration.
This is a certain point. Yes, absolutely.
Yeah. Okay. So that's what the Mart algorithm will attempt to do that.
Yes, so you have a number of certain points. So this one, it would be a point.
I wouldn't call them certain.
Well, near certain, quasi certain.
Better estimated.
Yeah, and then all the pixel values along the line where there is no intersection would be the estimation to the best of our knowledge. But again, the only values that we have access to are the values at the detector's end.
Correct.
So when you're doing the interpolation, Vahid, what I'm saying is that you should not access the pixel value. You should only access the detector value.
Oh yes, of course. We haven't gotten we haven't gotten to that step yet.
My assumption was we are doing after the estimation of the line of every line. So I wasn't going one step earlier, which Mart is doing and is detecting or estimating those pixels of a line. I assume that we have some estimation for every pixel of a line, some estimation. So after that, what we are going to do with in between those lines, if we are going to actually deal with the line estimation as well, that would be another problem again.
Yeah.
So maybe here Dr. Gordon could better make a point that if we are going to do the first part as well or not, or we are just doing the part after the Mart estimation.
We have to keep making it more and more realistic. So soon we give up the butterfly.
But remember, it's not. You can carry on using, and I'm sure that he's making a joke with the giving up the butterfly. Butterfly is an example. The only thing that I have concern with is the fact that you do not have access to the pixel value of the butterfly. You have so all you have access to is the value at the detector's end. So you'll have the detector's end, and then you will have the depending on the places where the projections being done, you have access to only this particular single value. And based on that, you should do the reconstruction rather than. So this would be your image similarity measure rather than comparing the pixel value of the original image and the reconstructed image.
Yeah. By the way, let me finish this here. That is correct, but the real problem is going to be three-dimensional.
Yeah.
And this gets more difficult, but I think the principles will work.
Yeah, it would apply. It would be more time consuming, but the principle is the same. So in a way, so you can have, and this is what we've talked about in our paper, because we didn't want to lose the image similarity. So we have two error measures which you can keep in your analysis, Vahid. When you're doing the analysis, that will give you a very good insight. So one is the image similarity, and the other one is the similarity of the detector ends value. So the one that you will be working on is the detector ends value. So let's call this E1 error, because this is the error that you basically E1 error. This is the error that your system has access to, and on the side you can have the image similarity distance. You can call that Euclidean distance difference between the reconstructed image and the original image E2, and then you can plot them individually, but not to use E2 during the reconstruction process. Only use E1.
We can say from a actually machine learning point of view, the first one could be a supervised, but the second one usually is a non-supervised algorithm that we are dealing with.
It is supervised, but the supervised version comes from the E1 value, which if you have a large number of projections, then you are guaranteed to find you're guaranteed to have an E1 and E2 going down together, more or less. But if you have smaller number of projections, then E1 and E2 will be very far apart. And you can have an E1 equal to 0 that is not representing of the original reconstruction.
And maybe a real data set could help, could be really helpful, because one thing I'm not sure of, one problem I mentioned earlier is the width of every beam that is in detail. We are usually dealing with some problems like this. The other problem is actually how many, as you mentioned, how many beams in the real world, how many usually beams are usually going to be used. So how much data we usually have at the end, at the detector point. These are maybe some questions that with a realistic data set could be answered very well. And I asked many times from Dr. Gordon that if it could be possible I could have access to a realistic data set, but maybe in the future we should have something like that.
Yeah, the only way to get real data is to take a dead body and cut it up. And then you cut it. This has been done actually. There was a project, a couple of decades ago, on reconstructing two prisoners who died, one man and one woman. And they sliced them up and they x-rayed all the slices. Okay? So that's the only data set I know of that's going to be realistic.
Yeah. But from the technological, from the actual research perspective, it would not be as important at this stage having access to these data sets.
I agree.
If you assume each ray to have the width of 1 pixel, that's more than enough, because you can always change that line of code to cover 2 pixel and make some tweaks, and then that would update the program. So that's not important at all at this.
No,
at this
actually,
stage.
I'm saying because I need to actually have an idea of the real data in the world. So I could, for example, consider how much data usually I have at the endpoint at the detector level. How, for example, as I said, how wide could be a line and something like this. Just having an idea of the real world problem. So maybe, as you said, it's not much important for now having a complete data set, but only for having an idea.
If I can interject here, I think one easy way to go about it is to assume that you are trying to project the smallest number of rays and get the most accurate reconstruction.
Yes.
So that is the goal. So even if the real world data would tell you you can project 1,000 ray and get the data, that is not the holy grail. So you'd like to reduce that to 500. If you can reduce that to 100, then even better. So try to reduce the rays to as little as possible and get as good reconstruction as possible. I think that's the goal, and it's going to be a research.
Let me give you some context for this. If you consider women as a whole, only 1 out of 8 has breast cancer during their life. Okay? So that means that if normal women are coming in, you want to give them at least the least amount of radiation, which means the smallest number of lines, in our case, so that they get a very low dose before they're sent home. Okay.
Okay. All right. Yeah. I think we'll end it here. I want to move on to Hussain. He has some things he wants to report on here. All right, Hussain, why don't you share your screen?
Okay. Mohammad, perhaps you can, if we use the MART algorithm for reconstructing the lines, perhaps you can help work with Vahid or something, or use Boyd's to try to fill in between the lines.
Yeah, well, actually, swarm intelligence and evolution computation can be used even with this structure. So for
oh, really?
For imprinting, because this is what I was trying to get to when I was talking about creating an error that represents the problem in the real world rather than the image similarity, because the reconstruction can happen in this form. So it wouldn't be the process would not be difficult. The result will be unknown, but certainly they can be used, and it would be a high dimensional problem, but I think it's absolutely worth exploring, and that's why I talked about the E1 error and E2 error, because this is where they would become quite relevant in terms of quantifying the reconstruction.
Okay, now I have a problem which I haven't been able to solve. Are any of you familiar with Perlin noise? Has anyone worked with Perlin noise?
I haven't worked with it. I know a little bit about it.
Okay, the problem is there's one paper which claims there are 3 types of normal tissues in breast, and each is characterized by Perlin noise with different parameters. And I cannot figure out from the paper which parameters go with which tissue type.
Right.
Okay. So
have you tried writing to the authors?
They don't answer.
Yeah, that's it. That gives us the answer.
So Hussain,
it's not a well-written paper.
Yeah, Hussain,
that explains it.
Are you ready?
Excuse me. Yeah, thank you so much. Right. Yeah. Hi. Nice to meet you all. My name is Hussain. My name is Saeed Hussain Ather. I previously worked under Bradley through Oral. I currently work. I finished my graduate studies, or I was doing my PhD at the University of Toronto in medical sciences, particularly in computational neurosciences, where I would analyze fMRI and EEG to understand the brain connectivity structure underlying schizophrenia as well as other disorders, emphasizing BCI, brain-computer interface technology, as well as more general applications of math, statistics, computer science to understanding neural and neurological data. During my undergraduate years at IU Bloomington, I had the honor of taking classes under many renowned. My undergrad was in physics, so I did study under great professors like Robert de Ruyter is one perfect example, and I at least had a few conversations with people like John Beggs, Olaf Sporns, if those names ring bells. So I'm coming to you right now to present with you a project that I'm working on. It's kind of semi-under Bradley, but more so my own independent research, where I'd like to start making contributions to OpenWorm and to DevoWorm. This is part of a lot of remote contractual projects that I'm working on here and there. I can also just let you know this fall I plan on actually going back to school to get my master's in data science part-time through Georgia Tech to really, really refine a lot of those mathematical and computational skills, more so as they can apply to like very, very high-end careers in data science, AI, machine learning, etc., etc. So, as I understand, there are many. And once again, I do have a meeting in about 15 minutes. That's why I am trying to speak with haste, but I do want to, I do want to leave the room open if people want to chime in too. Excuse me.
Hussain, how about putting your email address in the chat?
Sure. Nice to meet you all. And you guys should follow me on Twitch because I stream my research on Twitch, and it's really cool. I'm trying to get Twitch off the ground for streaming science and programming. For those of you who don't know, Twitch is a platform mostly known for people streaming video games. But I got featured several years ago when I said, hey, why don't we use this for streaming science? And it was such a cool idea that they featured me in Science Magazine. And this is where I'm showcasing my journey into public source and open source. And I've even met a few other scientists here and there who are starting to use Twitch too. So if you want to see what I'm doing in real time, feel free to stop by whenever I'm live. Or like if you make a Twitch account and you follow me, it'll notify you whenever I'm live. But yeah, thank you so much. Right now, so I had pitched a few ideas to Bradley, some potential ideas for projects to work on. And ultimately, excuse me, I need to bring this up. All right, my computer always gets so slow when I'm streaming video. Let me, okay. Excuse me. All right, thanks. Okay, so I'm just turning my video off because it makes my computer easy. My computer gets a bit slow sometimes. But there were two potential ideas. I'll paste the summary into the chats really quickly. Two potential ideas that Bradley had given some good vibes towards, like some I pitched some potential ideas of what it'd be best for me to focus on right now regarding the projects, and two of them stood out in particular. These two, I'll post in the chat.
Okay.
Data fusion and integration. Yeah, I was posting in the chat. Thanks, guys. No, video is just off because it does make my computer a bit slower when I'm streaming too. Yeah, data fusion and integration, and adaptive simulation control, with a few broad ideas and general ideas on how I could contribute in those ways. I also do have access to AR and VR technology too. I have some practice with that. If we wanted to really go virtual with the virtual worm and push it to VR environments. But anyways, any sort of feedback of which of these ideas would be best for me to focus on, given the time and energy and efforts and resources I can offer. Any sort of feedback would be greatly appreciated. So thank you. Nice to meet you all.
Oh yeah. So yeah, that's good. I think, like I said, I think the data fusion and integration project would be good because we've done some integration of the data that we have, but we have a lot of data sitting out there. So we have a lot of microscopy data. We've done machine learning on that. We have electrophysiological data through OpenWorm, and I know that Vahid is interested in getting some of that for developmental stuff. So, being able to integrate that is always a good way to, find a new paper or find a new sort of spin on things, because there's so much bioinformatics out there. It's just putting it together is really the challenge. So I think that's probably the best way to do this. And of course, we have people who are doing like machine learning and they're always looking for data sets. So, I mean, but there is one challenge to data fusion, and that is getting the right context. So if you have comparable things, not apples and oranges. So like, for example, if I had microscopy data on embryogenesis and I had this process of embryogenesis, I would want to find data, say like electrophysiological data that I could map to different stages of development. So I can't just throw them together. I have to kind of make a framework for that.
Right, and especially solving that problem is a difficult problem central from mathematics to areas of neuroimaging, neuroscience, and bioinformatics too. Like how can we produce the images that we want to produce from the data itself, but more specifically, FFTs, convolutional integrals. In what way can we use them in the most practical manner? So
yeah. And then adaptive simulation control. So that's interesting. I don't know. Reinforcement learning algorithms are probably a lot better than like standard machine learning for that. I mean, at least in my opinion. And then of course there are also different control algorithms that I don't mean that if you want to get into that would take a lot of sort of training and yeah. So I mean, we might try with reinforcement learning algorithms. I think we've been talking about that a lot in the other group that we do, and it's like there's a lot. It's very hot actually as a topic, people are really kind of trying to drive reinforcement learning forward. So that might be interesting with respect to like some of the OpenWorm simulations that we have now. So like, we have the 3D worm, which is a browser, and we have cybernetic, which is like a biophysics simulator. So you can see the worm like crawl through different media, and you're just simulating the physics of the media and the physics of the worm. So that's all that is. But you don't have like a brain. So that's where maybe reinforcement learning comes in.
They're pretty smart, despite not having a brain. Yeah.
Well, they have a brain, but it's like the simulations don't have any brain. They're just kind of physics interactions. I mean,
right.
Yeah.
I meant more so the source of the cognition, whether it's rooted in their networks versus
Yeah.
Well, thank you.
Yeah, but I mean, like, I think the and then like with reinforcement learning, I wouldn't jump into that like try to be as sophisticated as possible right away. I mean, you'd want to have like maybe start with a very simple problem, like for example, like with Breitenberg vehicles, which is something they use in cognitive science. They model phototaxis, which is where they have an agent and there's a light source, and then the agent has to navigate towards the light source. It's just kind of the way that the internal neural network is set up in the Breitenberg vehicle. It can recognize light gradients, and so it just moves towards. And so it's not really intelligent, but I mean, it has like this, has this preference for a certain part of the gradient. And so it moves there. It's kind of like a single cell moving towards like a chemical gradient, one part of a chemical gradient. So this is it would be a very simple problem to work on. You could like kind of perfect the algorithm or see what kind of algorithms people have used for something like that, and then move from there. So I think, breaking the problem down into like these very simple toy problems.
Yeah. Absolutely. I'd also like to strongly emphasize my experience I've gained through Blender, Unity, and Maya. Jesse, Bradley, and I were kind of very briefly last night talking through Slack actually how AI researchers are embracing 3D. They're all talking about how they're taking advantage of 3D software for their simulations, for understanding, say, like reinforcement learning agents in 3D spatial environments, and moving to platforms like that and being able to take advantage of those software would be ideal as well. So yeah. So once again, I have a few minutes, guys. Any feedback is appreciated. Feel free to email me with anything. I'm on the OpenWorm Slack channel too. So yeah.
Yeah, well, thank you very much, Hussain. Yeah, I just wanted to get that in. And so any questions for Hussain?
Any final questions, thoughts, critiques? Yeah, so my thesis supervisor at University of Toronto was John Griffiths. He's an expert in neuroimaging and cognitive science, and we would work on the human brain. So a couple summers ago, I got involved through Oral, through Google Summer of Code, and have since been, looking for ways to get involved more thoroughly. So thank you all. Yeah. Thanks.
Nice meeting you.
So the final thing I'd like to talk about today is there's been some progress in the past week or so on foundation models for biology. And so foundation models, I've really had trouble trying to get my head around what exactly a foundation model is, but I'm going to go through the Wikipedia page on foundation models and then go through some of the new foundation models that have been proposed and then an institute that's working on this problem. So the Wikipedia page for foundation model defines a foundation model as a machine learning model that is trained on broad data so that it can be applied across a wide range of use cases. So this is, I think we had a proposal a couple years ago on a general model, a general biological model in the group. And the idea was to train it on a lot of different types of data and be able to use a model to go across different types of microscopy data from C. elegans to human to whatever. So that's kind of, this sort of generalized model. Usually machine learning models require very specific training on one data set or another data set. But a foundation model, the way it's being proposed, should be applicable to a wide range of use cases. Stanford actually proposed one a while back, their Human-Centered Artificial Intelligence Center. They were the ones that popularized this term. And whether it's just a matter of creating a term for people to use and then, overselling something, I'm not really sure. But this is the way it's kind of coming together. So foundation models use very broad models, this broad class of models. So early examples of foundation models were language models like Google's BERT and OpenAI's GPT-N series, so GPT-3, GPT-4, and so forth. Beyond text, foundation models have been developed across a range of modalities, including DALL-E and Flamingo, and Music Gen for music, and RT2 for robotic control. So there are a whole host of different types of foundation models that we might be able to use in different domains. There's actually a part on the Wikipedia page on definitions of foundation models. We're looking at the Stanford Institute for Human-Centered Artificial Intelligence. They have their Center for Research on Foundation Models. They coined the term foundation model in August 2021 to mean any model that is trained on broad data that can be adapted to a wide range of downstream tasks. Where they synthesized this from pre-existing terms, large language models were too narrow, given the focus is not only language. So basically it's a large language model, but it's including other types of data and other types of function. Self-supervised model was too specific for the training objective, and pre-trained models suggested that noteworthy action all happened after pre-training. They wanted to emphasize the intended function of the model, which is where, we want to look at the function over something like the modality or the architecture or the implementation. Well, all of those three things are important. The function is the primary goal in a foundation model. So the US government has a definition. They've defined a foundation model. This is the executive order on safe, secure, and trustworthy AI model that is trained on broad data, generally using self-supervision, contains at least tens of billions of parameters, and is applicable across a wide range of contexts. The AI Foundation Model Transparency Act, which was proposed in 2023, defines a foundation model as an artificial intelligence model trained on broad data, generally uses self-supervision, generally contains at least 1 billion parameters, and is applicable across a wide range of contexts, exhibits, or could easily be modified to exhibit high levels of performance at tasks that could pose a serious risk to security, national economic security, national public health or safety, or any combination of those matters. And then, of course, the European Union has their own definition, which is an AI model that is trained on a broad scale, or on broad data at scale, is designed for generality of output, and can be adapted to a wide range of distinctive tasks. And the UK has even another definition, which is a type of AI technology that is trained on vast amounts of data that can be adapted to a wide range of tasks or operations. So I think you can see the commonalities between the definitions. Foundation models constitute a broad shift in AI development. Foundation models are being built for astronomy, radiology, genomics, music, coding, and mathematics. So the genomics one is this reference 10, and that's this Gen SLMs, genome scale language models reveal SARS-CoV-2 evolutionary dynamics. This is a BioRxiv article that talks more about how they're applying foundation models to, I guess, virology and genomics. So their aim here is we seek to transform how new and emergent variants of pandemic-causing viruses, specifically SARS-CoV-2, are identified and classified by adapting large language models or LLMs for genomic data. So, you can build a large language model for something like English. We know that. That's what GPT-3 and GPT-4 do. You can build large language models for languages like Swahili. There are other smaller languages that you can use to build large language models for. So a lot of Native American languages, for example, where they're trying to preserve the languages. You could use a large language model to characterize those languages and generate text. You'd have to train it on a specific data on a specific corpus. And you can do this in parallel with something like an English LLM that would be able to translate terms and things like that. But you can also do this with genomics data. You can do this with proteomic data, and you can do it with DNA. So we have sequence data, and we can look at RNA sequence data as well, and look at the structure of the data, and we can generate sequences, which is the crucial part of this. It's a generative model that we can use. So by adapting LLMs for genomic data, we build genome scale language models, or GenSLMs, which are genomic SLMs, which can learn the evolutionary landscape of SARS-CoV-2 genomics. So they're actually proposing that this evolutionary landscape, which is something that in evolutionary biology we're very interested in, because we're interested in all combinations of a genotype. So if we want to look at the evolutionary landscape, say, of C. elegans, we might take the C. elegans genome, and we might put it in the context of all combinations of that genome. Now, needless to say, that's a very highly intensive computational task, but that's something we can then explore and find not only different, where different variants are placed in that landscape, but also latent variants that maybe don't exist in the world, where we can't observe them directly. So we can simulate them and simulate paths from one genotype to another. So in this case, we have SARS-CoV-2 genomes, which aren't very big, so we can actually simulate this probably quite effectively in an LLM. And then the idea would be you'd be able to generate, with a prompt, you'd be able to generate a certain genotype. By pre-training on over 110 billion prokaryote gene sequences and fine-tuning a SARS-CoV-2 specific model on 1.5 million genomes, we show that GenSLMs can accurately and rapidly identify variants of concern. So we can actually prompt this with different things. We have this database of all these sequences that we can look through. Thus, to our knowledge, GenSLMs represent one of the first whole genome scale foundation models, which can generalize to other prediction tasks. We demonstrate scaling of GenSLMs on GPU-based supercomputers and AI hardware accelerators utilizing 1.63 zettaflops in training runs with a sustained performance of 121 petaflops, in mixed precision and peak of 850 petaflops. We present initial scientific insights for examining GenSLMs and tracking evolutionary dynamics of SARS-CoV-2, paving the path to realizing this on large biological data. So these are very big data type things. So you're able to scale them up. So, you can work on a very large space of viral phenotypes or viral genotypes. I guess they'd also be phenotypes in this case. But you'd also have the ability to build larger models for maybe something like C. elegans. But the memory requirements are going to be pretty substantial. So that's one example of a genomic foundation model. And so this is how they define foundation models. After a foundation model is built, it can be released in one of many ways. There are many facets to a release. The asset itself, who has access, how access changes over time, and the conditions on use. So these are all things that we worry about in open source models, and releasing them and managing how they're used and managing sort of the different parts of the model. So we don't want to just open it up to anyone. We want to be able to control some of the aspects of it. We also want to control the training data, so that's a very important part of it, especially with like medical data, but also with just biological data. It's hard to keep the model relevant if you just kind of train it on anything. So we need to have sort of this auditable system of saying these are the data sets in the model. This is what we have that we're currently training it on. If we specialize it in any way, we need to be able to record what those data sets look like. And I think in the meeting today, we saw that we have needs for sort of understanding what our training data looks like. It very much affects our results. So when a model is released via an API, users can query the model and receive responses. So there's that querying aspect. It's some sort of text query, and then we end up with something coming out as a result. but we cannot directly access the model itself, so we can't see the weights necessarily if we're using an open source version of it, but we can do, use a query. It's kind of like the way a lot of large language models work online. If we run it online, we might enter a query into a website, we might get a result. Maybe like if you're using ChatGPT, you might get a block of text, you might get some images from something like Stable Diffusion, but you can't see how the way it was assembled and what the weights were in the model and so forth. So this is, of course, the sort of the limitations of one of these foundation models is you can't go in and under the hood and inspect what's going on, or even modify it as you need to. Now you can run it on your own machine or your own hardware, but the problem is, of course, is that you need to have the right, you need to have sufficient computational power. And so a lot of times these models are hosted in the cloud, so that's a limiting factor for a lot of research groups. So some open foundation models are GPT-4, Palm 2, Llama 2, and Mistral. So these are just different general foundation models, large language models. And so, the thing is that when open foundation models, so actually foundation models, one of the problems we have is that because they're so general, people can misuse them a lot. And so with biological models, it's an interesting problem. On the one hand, you have access to these kind of, high-end models. You can put in images and you can get out a result. But on the other hand, if it's not transparent, we don't know exactly what the appropriate conditions for use are. So with a general model, I can train it on, say, C. elegans data for a C. elegans embryo. And I might try to analyze a Drosophila embryo. And of course, my results on the Drosophila embryo are not going to be very good because it's a different, the developmental process is a bit different. So it might recognize some aspects and not others. Now, it's kind of like misapplying statistical models. So statistical models can be misapplied if you violate the assumptions of that model. And so it is with machine learning models, and especially with foundation models. If there are certain underlying assumptions, depending on how they're trained very generally, but at the same time, they have a lot of limitations that can arise from the choice of things that are put into the training set. So we might end up making mistakes or violating assumptions that we weren't aware of. So this is a problem. And so we want to be able to balance sort of the transparency with the ability to interpret the result and so forth. So this is what's going on with foundation models in general, and I just gave you an example of a genomic foundation model. So with that being said, there's this foundation model that came out recently. So this is a blog post from the Stanford Human-Centered Artificial Intelligence group, and this is reflections on foundation models. So they launched a Center for Research on Foundation Models, and in this blog post, they discuss why these models are so important and reflect on the community response. So they define at Stanford, they define foundation models as models trained on broad data, generally using self-supervision at scale, which means that you don't have to train the model for your specific instance. You can just use the model and you train it on enough data on the back end, and on the front end you can put in different types of input data to try to get an analysis out, and it's basically self-supervision. You don't need to have like specific data sets. These models, which are based on standard ideas in transfer learning and recent advances in deep learning and computer systems applied at a very large scale, demonstrate surprising emerging capabilities and substantially improve performance on a wide range of downstream tasks. Given this potential, we see foundation models as the subject of a growing paradigm shift where many AI systems across domains will directly build upon or heavily integrate foundation models. This incentivizes homogenization. The same few models are repeatedly reused as the basis for many applications. Such consolidation is a double-edged sword. Centralization allows us to concentrate and amortize our efforts. So we have single models that we're working to perfect on a small collection of models that can be repeated and applied across the applications to reap these benefits. So this is like building the infrastructure for like the standards in a field. But of course, centralization also pinpoints these models as singular points of failure that can radiate harm. So we might have problems, in the cases of biological models, there isn't really a social risk, but there is this risk of misapplying the model, violating the assumptions of the model, and so forth. So there are a lot of ways in which we can screw up using foundation models, even though it seems like this is sort of the holy grail for a lot of our modeling efforts. So, we have a lot of tools out in the world, especially Hugging Face and some of these other large corporations that are trying to develop foundation models. So foundation models aren't something that small groups can generally do, but I'm going to talk about an institute that's doing this though. So okay, so they have another interesting point here, and this is with respect to grounding models. And so they say that foundation models can and increasingly should be. So they have the section here on grounding models, and it's interesting how they connect this to embodiment and some of the things that we talk about with embodied cognition. So foundation models can and increasingly should be grounded. Perception, interaction, acting in a physical 4D world, and acquiring models of common sense physics, theories of mind, and acquiring language grounded in this world are important components of AI. This is from Malik 2021. We can get to the bottom and look at that. That all involve or require grounding. Given the importance of grounding, we draw attention to existing efforts that successfully build foundation models with various forms of grounding, such as CLIP, which is trained on image-text pairs on the internet, and Merlot, which is trained on YouTube videos with transcribed speech. So there are a lot of, kind of models that are multimodal. You have text, speech, and then images and video. Further, grounding can also be achieved by integrating foundation models with other approaches in AI. So Piglet is, it's an acronym, cute acronym, is a recent example that grounds linguistics form encoded using a pre-trained language model with a neural model of physical dynamics. So you're now connecting language and language learning with physical dynamics. Foundation models are not just large language models. Foundation models can also be trained using images, video, and other sensory and knowledge-based data, and some already are. So they have a separate report from this. We underscore grounding is critical to how foundation models will evolve in computer vision and robotics. So they use this aspect of grounding a model, or there's this idea of grounded cognition, where grounding concepts in other things. So there's a multimodal aspect to this. So in a biological model, we might have a list of terms or like a corpus of linguistic terms, jargon. It's very famous in a lot of scientific fields that you have your own set of jargon. And then you have your own set of data, which could be image data, it could be electrophysiological data, it could be sequence data and the like. And so all those things are put together into a model. And so we already do this kind of with labeling, but this is a more sophisticated way of doing it. So now I'm going to talk about two papers here. This is the first paper, Sequence Modeling and Design for Molecular and Genome Scale with Evo. And so Evo is this new foundation model that I'm going to talk about. These people are associated with Stanford University, what they call the ARC Institute, which I'll talk about in a little bit, something called Together AI, the Chan Zuckerberg BioHub, and the University of California, Berkeley. So a Bay Area group of people, very Bay Area flavored because they have a number of startups involved. And so these are the people behind this Evo model. So they're interested in going from the molecular to the genome scale. So they're not working on phenotypes, they're working on processes necessarily. So let's see how they do on this. So the abstract reads, the genome is a sequence that completely encodes the DNA, RNA, and proteins that orchestrate the function of a whole organism. So this is what they're trying to bring together, some of these molecular and genomic aspects of the phenotype and of the organism. Advances in machine learning, combined with massive data sets of whole genomes, could enable a biological foundation model that accelerates the mechanistic understanding and generative design of complex molecular interactions. We report Evo, a genomic foundation model that enables prediction and generation tasks from the molecular to genomic scale, using an architecture based on advances in deep signal processing. So they're working on signal processing techniques. We scale Evo to 7 billion parameters with a context length of 131 kilobases at single nucleotide byte resolution. Trained on whole prokaryotic genomes, Evo can generalize across three fundamental modalities of the central dogma of molecular biology. So these are described in the paper: to perform zero-shot function prediction that is competitive with or outperforms leading domain-specific language models. So again, in Evo, they're using language models, but they're applying it to these problems with, in this case, prokaryotic genomes. Evo also excels at multi-element generation tasks, which demonstrate by generating synthetic CRISPR-Cas molecular complexes and entire transposable systems for the first time. So they're actually generating they're not only training it on these prokaryotic genomes and generating sequences, but they're actually able to generate CRISPR-Cas molecular complexes and transposable systems. So this is very important for synthetic biology and for bioengineering. If you need to create a construct, for example, usually people design this with keeping the promoters and the sequence, the target sequence in mind, and they have to put it together, and it's a pretty painstaking task. And so with a foundation model, you could just simply design them by generating what you need, the needs of what you want to do, with some sequence that's generated by the model. And of course, you can specify function in the model. You can train the model with functional annotations and make it even better. Or at least that's the hope. Using information learned over whole genomes, Evo can also predict gene essentiality at nucleotide resolution and can generate coding-rich sequences up to 650 kilobytes in length. So we get these fairly large sequences, 650 kilobytes. It's actually a pretty big chunk of sequence. It's something that we can definitely use in building constructs or identifying contigs or whatever we want to do. It's definitely enough to really kind of make it biologic or bioinformatically useful. And so this is where coding-rich sequences, meaning that it can identify coding regions and generate parts of coding regions and so forth. So this is important in terms of like sequencing data, because a lot of sequencing data is you're trying to build consensus sequences and try to build different types of annotated genomes, and this can help with that process for individual organisms. Advances in multimodal and multi-scale learning with Evo provides a promising path towards improving our understanding and control of biology across multiple levels of complexity. So what they're doing here is they're building a foundation model for genomes, for identifying coding regions, identifying promoters, identifying things that could be used for bioengineering or for bioinformatics and the like. So we haven't built up to the phenotype, at least for prokaryotes or for viruses. We can do this for RNAs, we can get phenotypes. But for things like C. elegans, we cannot get a phenotype from this. But it's very much bioinformatically useful, as I said. So they kind of go through this. So I'm not sure if this is something that's available to the public. I think they're just reporting on this pre-trained model that they're using. So they're actually getting, they're building these language models. So in this figure here, they show what they call a long context genome foundation model. So they have this sequence. They have a regulatory DNA model where they have a promoter, they have a coding sequence, they have a promoter, and a non-coding RNA gene. And so they can take all these data and they can build a number of language models. They can build a protein language model, they can build an RNA language model, they can build a codon language model. From the coding sequence, you can build a codon language model, which basically takes the coding sequence and builds a series of codons. And of course, we have these alternative open reading frames and alternative sequences that result from where the open reading frame starts in the coding sequence. So this is a generative problem that we can actually solve pretty well, hopefully, using the codon language model. It takes all the possible codons and it puts them together in a generative fashion. And given the sort of the grammar of what this gene produces in terms of, or what this coding sequence produces in terms of transcripts, we could, predict what this is going to look like. From the codon language model, then we can build a protein language model that predicts the protein sequences or the possible protein sequences. And again, this is a matter of taking codons and turning them into amino acid sequences and then predicting some protein sequence. So you have another language model that involves the rules of proteomics or amino acid sequences. And so we can put those together as well. And, this is not perfect, but it gives you a starting point. It's basically solving this generative problem that we've had in biological systems whereby we can translate a gene in many different ways, and we want to be able to predict which ones are most likely. So then the non-coding RNA gene then can produce an RNA language model. That RNA language model then is just basically predicting the RNA sequence and the secondary structure that results. So they build a model using likelihoods. So again, this is using a lot of bioinformatics and prediction. So this is how they pre-train these genomic foundation models. And this is on a prokaryotic model system. So we're using prokaryotic genomes where we have a lot of single genomes, and we can do this very well. And then we can, of course, have a compute optimal scaling here, and they're comparing it to other approaches in this graph G. So this is this is actually, I think, a blog post from their institute, where they're from. So this is the ARC Institute, and this is their blog post on this. So this is Evo, long context modeling from molecular to genomic scale. This accompanies the paper that I just talked about. So they kind of talk about how this is trained. Evo is a long context biological foundation model. So they use they use context from sequences based on the striped hyena architecture. So we talked about hyena in another meeting like last year. And hyena is a way that they're using a language model to predict DNA sequences. So there's this whole hyena architecture, and this is the striped hyena architecture. And this generalizes across the fundamental languages of biology. So in this case, what they're doing is they're building models for DNA, RNA, and proteins, as we saw in the paper in Figure 1. Evo is capable of both prediction tasks and generative design, from molecular to whole genome scale, over 650,000 tokens in length. So, they're using individual nucleotides as the tokens, and they're building a model from that. Evo is trained at a nucleotide byte resolution on a large corpus of prokaryotic genome sequences covering 2.7 million whole genomes. So they have to use 2.7 million whole genomes as the foundation for this foundation model. So that's a lot of sequences. And of course, in prokaryotes, you can have those kind of genomes. In other organisms, probably not yet, but we may get there. But the basic point here is that it takes a huge amount of training data to do this. So the striped hyena architecture is a deep signal processing architecture, which is designed to improve in efficiency and quality over the prevailing transformer. So they're building upon, they're trying to get beyond like the transformer type model, and they're using this sort of deep signal processing architecture. So Evo 1 was collaboratively developed together by the Together AI and ARC Institute. So we'll talk about the ARC Institute in a minute. But I want to highlight that this is the architecture that they're using. So this is a model of nucleotides here. We have our A, our C, our G, and our T. So adenine, cytosine, guanine, and thymine. And then we have probabilities for each. So this is like in bioinformatics where you try to predict the next nucleotide in a sequence. And they occur at a certain probability, and so we can actually put probabilities on those. And the striped hyena model means that it's building all these different sequences. So the input sequence is down here. You have an input sequence. Sometimes it has gaps. Sometimes you want to generate alternative sequences. And from that input sequence, you can predict, or there are going to be a lot of input sequences, but you can predict what the transition probabilities will be at any one position along that sequence. So when reconstructing a new sequence, A might be likely maybe at 0.5 likelihood, C might be likely at 0.1, and so forth. And so, of course, the next choice in this example would be A, most likely, but it could be C, G, or T. And so we can do this, site by site until we get our sequence. We have these different aspects of hyena and what they call rotary attention. So I'm not sure what rotary attention is. It should be in the paper if you're interested. But it maps it to this hyena operator and this GLU, which is the general language unit, I guess, and then it goes out. This is where you have the signal processing aspect. So you have where you're mixing sequences and channels. So you have this convolution step, long convolution step, and then there's an output. So this is a pretty sophisticated architecture. The model actually is available on Hugging Face, and the link is here. I don't have the link, but you can go there and probably search for this architecture here, the Evo architecture, and you should be able to pull it up. And also in the GitHub repository that they have in this link. So I'll put this in the description of the video, this blog post, and you can go to those resources if you want. It will be made available via the Together API and Playground soon. In addition to model weights, we are also excited to share intermediate checkpoints. We will be releasing the training dataset, Open Genome. So they're going to release the dataset in coming days, and I captured this earlier this week, so it should be available now. So there's this dataset, Open Genome, and this has 2.7 million publicly available genomes for prokaryotes, and that's the training set. So they're releasing their training set. They're releasing their code and their architecture. So by the standards of foundation models, this is actually pretty transparent. So this is, and then they ask the question, and we always ask the question in machine learning, probably erroneously, but is blank all you need? So in this case, is DNA all you need? And so that's the sort of cheeky question they're asking. In biology, everything starts with DNA. Genomes carry an entire set of DNA to make a complete organism. And so, I don't think that's going to solve all your problems. DNA, if you want to eat a cheeseburger, maybe, but if you maybe want to build a phenotype, no. So, this is, again, foundation models are interesting because they try to kind of be very inclusive in terms of all the data they're bringing in, and they try to make these very general predictions across data. But again, if we're trying to build a complex organism, this is maybe just a very, very early starting point. So that brings me to the Arc Institute. So the Arc Institute is this institute where it's a new institution for curiosity-driven biomedical science and technology. And so they're headquartered in Palo Alto, which is where Stanford is, near Silicon Valley. ARC is a nonprofit research organization founded on the belief that many important scientific programs can be enabled by new organizational models. ARC gives scientists no strings attached multi-year funding, so they don't have to apply for external grants, and they're interested in complex diseases and biology. So that's where they're coming from. Their tools, they have a series of tools here. So software and tools, they have Evo DNA foundation models. They have genome engineering tools like Cas13D. They have this design tool, and then ScreenPro tool, which is a tool for flexible pooled CRISPR screen analysis. So they have these genome engineering tools and these machine learning tools. And so that's all I have to say about that. Hope you learned something, and especially if you're interested in GSOC, maybe we can have more discussions about this with respect to your projects.